এটা কম করনি না very good evening to all our friends INE fellows and others in this lecture series, 51st lecture series being conducted today, and the present lecture is being organized by a group of institutions, that is INE Bhubaneswar chapter, IIT Bhubaneswar, NISER Bhubaneswar, then IMMT Bhubaneswar, then the Shiksha and Anusandhan University. Shiksha and Anusandhan University and IEEE Bhubaneswar section. So in this series of lecture, today is the 51st lecture, and it will be given by Professor Durga Mishra. Professor Durga Mishra is a professor and chair of Department of Electrical and Computer Engineering, New Jersey Institute of Technology, Newark, USA. His current research interests are in the areas of nano-electronic devices and circuits, especially in the area of nanometer, CMOS, gate, stacks, and switching devices. He is fellow of IEEE. He is a distinguished lecturer of IEEE Electronic Devices Society, EDS. He is also a fellow of Electrochemical Society, ECS. He received the Thomas Cullinan Award from the Dielectric Science and Technology Division and the Electronic and Photonic Device Division Award from ECS. He edited and co-edited more than 50 books and conference proceedings in his field of research. He has published more than 200 technical articles in peer-reviewed journals and in international conference proceedings, including more than 100 invited talks. He has graduated 20 PhD students and 55 MS students. He received the MS and PhD degrees in electrical engineering from University of Waterloo, Ontario, Canada in 1985 and 1988 respectively. Now, a short abstract of his lecture is data conversation, storing in volatile memories, transmission and computation impose high energy consumption, latency and memory bottleneck. To achieve energy efficiency and new low power nanoscale devices are required for the integration of sensing and in-memory computation to efficiently enable artificial intelligence on resource-limited systems. Resistive random access memory devices are currently being investigated for a possible implementation of artificial intelligence hardware through in-memory computing. The electrical performance in these devices depends on the dielectric deposition process, precise selection of deposition parameters, pre-deposition surface treatment, and subsequent thermal budget. The talk will discuss the ReRAM device with hydrogen plasma treated HFO2 that have shown low power switching and good conductance quantization with programming pulses, operation and quality, qualify them to be used for in-memory computing. Engineering the distribution of defects on oxygen vacancies near the top and bottom electrodes has a significant impact on reducing the switching power and improving the multi-level cell MLC characteristics of the device. So, friends, so now actually we'll request our distinguished speaker, Professor Durga Mishra, to make his presentation, and it will be followed by question and answer. Professor Mishra, please.
Good evening. I'm just happy to be here. I graduated from here in Odisha, and I did my undergraduate in physics and master's in physics in Redensa College. Now then I went to IIT Delhi and then moved to Canada to do my PhD. So this is a research that I'm working on. We can share the slides now. So the technology is moving. You can close that one. सही तो एक ना लगा दो. So what I will talk about is low power devices for in-memory computing hardware, so which is a small part of my talk. First, I will talk about our university. The New Jersey Institute of Technology is founded in 1881, and we have around 13,000 students on campus. We are a R1 university, that is research intensive university, that is only around 100 universities in the United States are R1. And it's located very close to New York City. And we have around 170 million in research expenditures per year. And we have several research centers and sort of things that about the university. One point is university is spending $10 million, the internal money, to invest in the campus-wide artificial intelligence initiative. As you know that everything we have to do in artificial intelligence, I will talk about that a little bit. That is both in research as well as in education. So the thing is, my talk, the outline is I will talk about some of the recent technology advances along with the historical perspective. Technology in the sense the IC chip technology. And then we talk about how the chips are designed and the artificial intelligence hardware. And obviously, some new memory devices for the artificial intelligence hardware. Now, what we are doing in terms of manufacturing these devices, or you can say fabrication of the devices, so that they make the devices energy efficient for the in-memory computing. In-memory computing also is required heavily for the artificial intelligence hardware. Then I will summarize this. As you know, this birth of the modern electronics started in 1947 with the invention of transistor, first transistor, which got Nobel Prize. And this is the picture of this on the left is the picture of this first transistor, but that was a junction transistor. And then in later years, we started this. In fact, the concept of field effect transistor was 1925. So this 2025 will be hosting the 100 years of field effect transistors. After the invention, we had the first metal oxide semiconductor field effect transistor was invented in Bell Labs in 1959. And then that time it was only N-channel transistors by managing electrons. Then managing holes, the P-channel MOSFET was year later came out. It was not as good by Fairchild. But the MOSFET I see also this both Bell Labs and RCA Labs, which came in 1960 also, the first integrated circuits with MOSFET came out. And that both the labs, Bell Labs and RCA Labs are in New Jersey. And then the transistor, which was formed as a planar transistor, became FinFET in around 2009 and 2010. And then people started doing this as the nanowire FET, the silicon as a nanowire. And that was very a little bit complicated. So then we came to nanosheet FET, the field effect transistor building silicon nanosheets. So those things, these are some of the pictures of those, the nanowire transistors and FinFET, these devices. And the new feature size of those nanosheets are actually 3 nanometer. So this is, if we go to 1 nanometer, we may have 6 silicon atoms. So now this is the first integrated circuit by Texas Instruments. It was by Jack Kilby, who invented it as only 1 transistor and 4 other devices, registers. And this one got the Nobel Prize in 2000. But today, if you look at, this is the Apple M3 transistors with 98 billion transistors in one single chip. So this is, and then the new devices that we have is the NVIDIA artificial intelligence chips, as the Blackwell RTX series they just released. They have 208 billion transistors in a single chip. But that is creating the idea how we can compact these chips or the transistors together. So as I mentioned about nanosheet transistors, I'll just briefly go over what is the state of the art as far as this month. In fact, the Taiwan Semiconductor Manufacturing Company announced that they will be, these are the technology they are going to be in production in 2025. So this is, as I said, the nanosheet transistor. This is a simple inverter with an N-channel and P-channel transistors. And the nanosheet transistors were actually developed completely separately. On the left side, you can see the bubble type of circuits. But now they are coming the CFET. CFET is the same, the complementary FETs, but that is integrated in 3 dimensions. You can see on the top, we have these nanosheets, and they are the animation shows how they can be stacked together to build those electronic circuits. And that is a simple inverter. Now, this is the complexity of a single chip. And you can see the nanosheet transistors are there on the bottom. And this is the state-of-the-art technology. These are actually after manufacturing of this. So the metal labels on the top called is BOL, that is back end of the lines. So back end of the line is all the metal interconnections there. And then the front end, which is nanosheet devices, and they develop excellent power consumption. As we discussed, this power is a serious issue. The power consumption will be there. And these are some of those things are currently already in the going to be in the market. The backside contact, which was not there before, that actually being introduced. In the bottom, you can see the IBM has published the 2 nanometer nanosheet devices. This is just release those devices. The another thing also happening is moving. Okay. So as you might have heard, there are 2D materials that's coming up. The 2D and something MOS2, and also there is another type of devices, both the NFET, or you can have the PFET on the tungsten disulfide. These are the materials, only the sheet of atoms, one-dimensional, so two-dimensional structure. They are not three-dimensional. And these devices are beyond silicon materials. They show excellent transistor characteristics, and those are being built right now, but they are not in production yet. But it gives a promise for ultra scaled transistors beyond the physical limit of silicon-based electronics. Because silicon-based electronics, if you want to scale down further, will not have that many atoms based on the silicon crystal. These are some of the examples that was presented. These are the papers presented in this year in December 7th, this year, by the TSMC group. And then another thing also is happening is heterogeneous integration. Since we are all using electronics in such a way, we will have many different companies designing chips and trying to integrate into, for example, in our iPhone, we have so many different, the smartphones, we have so many different components. So this is actually catching up now. The US government is spending more than $70 billion just to do the heterogeneous integration. That means you put all different functionalities. So one example of that is the chiplet technology. The chiplet technology, what happens before you send your design to, let's say, Apple, and they will integrate those things. Now you send your chip to them, and they will be integrated into a smart packaging. The smart packaging is also coming up, but how to organize these chips and what are the chips, all these, because then the companies can protect their intellectual properties and send the chips and the dimensions and the interfaces to the product-based companies. Like, for example, Apple, they can send it to for iPhone, different products. And how to put those, there is a lot of research going on how to just place those chips. Forget about optimizing the interconnections and all those things. There is another page. And if you can look at on the right-hand side, the complexity of level of multiple wafers are interconnected into the system. Develop these packets. They are not ceramic packages. They are all silicon packages. Silicon with metal, all the true silicon via the TSVs, and they have a lot of different type of interconnection technology has been developed. So this is just a flavor of things. I want to show you how this manufacturing units looks like. Right? You know, one of these machines that you see here is Intel's labs, manufacturing labs. This machine, the entire thing that you see is a huge piece of machinery that does only the one particular step of silicon manufacturing, for example, just etching. So if you look at all the etching and deposition and all those things that comes, this is a silicon cassettes are going in the vacuum chambers. They are moving on the black one on the middle of the picture. There are 25 wafers are moving around. So this is then cut and packaged and send the chips. So we are actually at a turning point. Chips are everywhere. As you know, these things, the computer centric was long gone. The mobile centric also being very standardized now. Now it's coming to the data center. Huge amount of data and huge amount of the Internet of Things. That means small devices and sensors. They spread all over the system, in the sense that billions of devices will be connected soon to do our tasks for any individuals now. So that there comes the artificial intelligence, AI. You might have heard this is a buzzword now. Everybody knows about that. And then machine learning is a subset of the artificial intelligence. Also, we have brain-inspired and computing that is coming out. So, this, if you look at everywhere, you can actually apply.
There is no audio.
Can you hear now, sir?
Yes, I can hear now.
Okay, excellent. So this is the, I was just talking about this big data, and there is, in this application, there are so many different applications now. For example, there is a graph processing, that is, we are doing for AI applications. So to optimize traffic data, optimize the flight parts of flight, tracking the flights. So those things are also is doing, so there is a lot of encryption that is coming up. So instead of doing in the normal computation that was we are familiar with, now many things are actually done inside the memory. As you can see, some applications are there for agriculture to this. Next. So the big data challenge next. You took it out that one? Okay. So there is a power wall. So first of all, we were just discussing before the seminar started, the amount of the power that we need for these data centers. So it comes down to build the devices or circuits or the chips that will consume the minimum amount of power. So low power design is a grand challenge now. And that is actually happening from the simple devices all the way to the architecture and the chip and systems level, and including even the software level, how to manage the software data sets to reduce the power. So all this comes, and then the frequency that we are operating all the devices, that actually has changed. So originally, all our computing was done by the Van Neumann architecture, which actually does, there is a direct link between the CPU, the central processing unit, and the main memory. So you transfer the data, you make a one step, CPU moves one step and stores the data in the main memory and gets it back, go to the next step. Similar things also the GPUs that can, the graphic processing units, a lot of parallel computing, but also interfaces with the memory. This particular architecture that is applied to all our computing system. It's very energy hungry data transfer and long memory access latency also, and obviously limited bandwidth because we have it has to go. There is a for fast processing you can have some cache memory, and then you can use your DRAM, that your memory that you have. So these are the things was very challenging and a lot of consumption of power. So now, if we can do this processing inside the memory, why not? So CPU sends an instruction to the main memory. It stores and processes everything inside the memory. That's what called in-memory computing. And that is actually coming up in a big way, so that data, that way we can just IoT devices, sensors, information that we can have, and you can finish those things in the memory. You can collect a lot of information to store and process. So the artificial intelligence hardware has one branch. You get the signals, you get the real value inputs like x0, x1, xn, and they are stored in something called the weights. So that's why the weights are actually a type of circuit that holds the amount of charge there. W0, W1, W1, and then finally you multiply and accumulate. That is called multiply, accumulate, or back structure. So the output of any neurons this is implementing the neural network chips is a nonlinear function of the weighted sum of the input. The neuromorphic computing is also similar, exactly same process. This neuromorphic computing, the brain-inspired computing. Only thing is the binary input that you receive, they are very discrete, and that is called the spiking neural network, or the normal artificial neural network or convolutional neural networks that is followed for a standard AI. So if you look at this, the accelerator, they are now called not the regular systems or the computing system, they're called AI accelerator. That means these are the hardware that is people are designing the chips. There is a completely custom type. So it will help or accelerate the artificial intelligence applications. So those are the chips that is being designed now. I think, as I mentioned before, we have Internet of Things, and we deal with them in the cloud. So if you send everything to a data center and process them, it is a huge loss of power. So many things can be done in the local, and only the important message can be sent to the cloud. That's what actually is happening. A different type of devices or processing in memory or non-volatile memory. Access memories. These are some of the chips that designed in our university, our faculty and students. Thanks. So another thing also in the design, I will mention you might have, everybody knows now, large language models in hardware design. That is extremely new concept that we can use and generate hardware. And we can generate hardware by just with hardware description language or creating hardware description language by using the large language model, which are used typically for AI applications. Or we can use the circuit simulator called SPICE, also using this. But this is actually focuses on generating the reliable circuits. Problem here is you got to start how to test this. That means you actually did that. Two things are the negative things is doesn't have the actual data set for reliability. That means the AI tool or AI, the ChatGPT or whatever tools that you are going to use, they may not understand what you are trying to do. There is nothing much there. Then there is no benchmark in analog domain, so that you can take a set of transistors or number of transistors and set of circuits, and then you cannot test them that your model is going to work. This is, and then it's costly, and then eventually if the human intervention will be there, then you come back to the square one. So what do we have? People are trying right now the data augmentations. That means how to create data set for this type of SPICE, creating SPICE node. This is one example. There are many other things that are going on in architectural level, transition level, as well as all the systems level. So the LLM actually first used through a Python environment, and that creates the data set. And then that is called the SPICE pilot, and it can be simulated using iteratively in many different and then we got to test this in the SPICE bench. There are a lot of universities have developed a set of benchmark circuits, and we test those things there. My student actually go back. My student actually working on this to build those circuits now. And we are collaborating with another university called Georgia Tech, Georgia Institute of Technology, to develop this type of software. Even those who are developing the CAD tools company, they are also collaborating with, for example, Synopsys, Cadence. They are giving us free software to implement this type of circuits. Okay, so next. So now a little bit about brain-inspired computing. You know, the human brain can do many different things from approximately. Power consumption is of human brain is only 10 to 20 watts. But if you look at the most sophisticated supercomputers, can require 2 to 3 megawatts just to process the simple functionalities of cat's cortex with 109 neurons and 15 synapses. The human brain can, it's not that easy, but it can consume 100 megawatts of power. If we do that, because we want to implement this. So the idea is, as I mentioned before, in math application, multiply and accumulate. This is we develop these called synapses, which are the weight, the W1, W2, and W1. And the neuron transmits the signal, the artificial neural network. And then there is a system that adds those things and sends to the next level. So to implement this, there are 8 transistors. Even NVIDIA chip that I showed it to you, they use 8 transistors to do this the weights, to store the weights. And that is a huge consumption of power. And that is called electronic synapse. And that is working in a sense that is efficient. That's why they have so many transistors. Because if you put 10 to 15, 10 to 19 neurons, sorry, the synapses, these are synapses. So synapses actually, I will just give an idea. What is in the synapse in the brain? Synapse gets signal from the neurons, but doesn't really fire the other neurons. And it gets the best example I give, that when the mosquito bites, initially you feel the pain, but your hand doesn't go and hit the mosquito. And the pain is excess. Then your hand goes and hits the mosquito. that actually synapse control that. Once the neuron sends the information to synapse and it crosses a threshold, then the other neurons are fired up and then action is. So what we are trying to do next? Trying to find this transfer all the 8 transistors to a single device. That is called a memoristor. That is actually because it's a simple register. That is the memoristor which works with the synapse. And because it has the same characteristics that I mentioned in the synapse, and there you can give the input voltages and you build those crossbar arrays to build this type of circuits. I will explain a little bit more. So the analog crossbar, this is the intrinsic MAC machine or multiply accumulate machine. It is just a simple device and it can do the crossbar next. Crossbar neural network, as I mentioned, and it will have also can be used in memory computing because this is the word lines are in yellow and the green lines are in the bit lines. So by activating, by controlling those things, we can get all the accumulated data from there. So this, you can see the signal comes in, and this is the module where we can build those. And that can be of devices of 10 to the power 19 synapses. Each individual device can be a synapse dimension. So this works actually, for example, this voltage comes in and C1 is the conductance. It sits, and that conductance is a variable conductance. If we can have 10 different conductances there, we can have 10 different weights, and it will also remember the things if we use neural network applications to remember and learn from this. But to have accurate values, you got to have correct conductance. This is a simple device that is done. You can add up all those devices. So our research, what I will be describing now, we'll be talking about how to build those little devices with a highly reliable and with extremely low power. That is the idea. So giving a little bit history of memoristor, it was unknown that we didn't know that the register can change its resistances. And so in 1962, there are some negative resistance in the thin films devices. And the problem was it was just publications. And 1967, the Pacific phenomena in titanium oxide thin film they found out. But it was also very interesting that the thin film can change its resistance and back, make it a conductance and become a resistor like this. So that was the first memory star by Dr. Chua. He developed in 1971. He showed that you can apply by applying electric field, you can actually change the resistance values and bring it back to normal resistance. In today's stuff from 2014 onwards, maybe thousands of publications have come out how it is, how it works. And the advantage of this you can have, as I mentioned, is extremely high density and very low power consumption, low voltage, and ultra throughput, and you can do in situ coding there. But it has a lot of disadvantages now, and people are trying to solve these problems. So the precision, for example, if you go for a particular resistance value by applying certain voltages, and it has to be precise all the time. So that is actually is a little bit difficult. Plus, all the crossbar arrays that we did, we have to build the digital to analog conversion and analog. So that also the circuit level, people are trying to optimize those things. And the routing is also another issue because if you have 15 or 19 synapses, you have a lot of metal wires to be interconnected. And these metal wires can also have voltage drops. And then, for example, if you have one device, we can program it to certain conductance, certain resistance. But if we have, by applying a voltage pulse for let's say 1 volt, But if you apply the voltage plus at the edge, it will not see 1 volt, say 0.9 volt or 9 volt, then it will have a different conductance value. So those are some of the issues we are doing. So this write and programming energy, how much energy it will consume. And then obviously the variations. Within the manufacturing, it is not possible to have all these 10 to the power 19 devices be exactly the same type, even though they are very compact. And these devices can be 3 nanometers and so that size, and they will be perfectly working. These are some of the issues. Now, the industry as well as the research labs are working very hard to optimize this by adding different materials and multiplying. So, I will show you some examples. So, this is one example of these things, the multiply accumulate device, electronics, so-called electronics stacks. So, this individual, we got to have a multi-level storage. That means we got to have multi-level conductance values, or we call it conductance quantization. That means you apply a simple pulse, or a pulse value, the repeat value, the pulse width, simply adjusting the pulse width. Time you apply the pulse, you can have a different conductance. That is the goal of this research. The PC website. So the non-volatile memory evolutions, we are all familiar with electronic flash memories. This is embedded flash circuits. And then also this resistive RAM, that we call it resistive RAM, because these are the resistances that can change the resistance value. And there is a magnetic RAM also coming up, is just applying a magnetic field, managing the electric power, the magnetic ferroelectric properties of this the conductance, then that will change. Based on that, people are working on this. But the E-flash that we are using now, for example, in our memory sticks, they're all flash memories, and they are stopped sort of at 22 nanometer. They cannot go smaller than that. Sometimes people have tried in 14 nanometer technology. Whereas if you look at this RAM or MRAM device, they can go to 1 nanometer dimensions. So, and also extremely low power consumption. So this is the distribution MRAM. If you look at the process companies, the non-volatile memories that we have, the NVMs, those are actually these E-flash. It's extremely complex to fabricate these devices. And this fabrication of these devices also, you cannot go to the smaller dimensions. They are obviously logic compatible, and writing speed also takes, writing speed is comparable to the magnetic field interference is a serious issue for have strong magnetic field in the flash memory, you may lose the data. And then the data retention, but this data retention is still a small issue for RAM, the resistive RAM devices. And the cells are actually, I will show you more details how this works. But this is actually, that's why there is a lot of investment by industries. This is the TSMC that presented this work. So they're going to invest huge amount of money to use RAM cells to build their circuits. So these are some of the devices that I mentioned, the STT and RAM devices. There is a PCM device that's called phase change memory. If you apply a pulse, it exactly like what's the synapse. It melts the silicon, the polycrystalline material. That actually changes the characteristics of resistance. To talk the RAM, it is simple because oxygen vacancies move around and form a line. That's why it changes its difference. Once the line breaks, then obviously I'll show you the details of it. So these are some of the devices that people are doing. The problem is who is consuming more power. The least power in this case is the RAM devices, but they are not highly reliable yet. And this is the phase change memory. The said that thing you can create a conductance quantization by just applying electric pulses. But as I mentioned, this contains the amount of power, and that's why it is. It started actually. There is a set of devices used. This has two states. One is low resistance, high resistance state. In low resistance state, you can have multiple resistance states. That's what they is so, but it's not highly reliable now, and then the company is getting out of the picture. So this is the basic principle of how it works. To get a fresh device, there are few defects. There are actually the oxygen vacancy. We use a dielectric. When you apply a pulse, suddenly it forms the oxygen or the oxygen moves, it forms a filament. That is called a conducting filament. And that is called the low resistance state. These conducting filaments you can make it fat. That means the resistance will still go down. But if you reverse the potential, then the conducting filament ruptures. Then it becomes to high resistance. So if you look at the thin conducting filament and thick conducting filament, by managing the voltage pulse, I will show you later, you can create the multi-level states of storage. Next. So to do this, actually, the idea is here people started using the hafnium oxide, which is being used in the transistor now heavily. All the including the nanosheet transistor I mentioned. But the hafnium oxide, the high quality hafnium oxide, initially gave a lot of trouble. It didn't have that many oxygen vacancies. So people intentionally created, they said, okay, we will make hafnium OX, which is less than 2. This normally hafnium oxide is hafnium O2, hafnium OX, so it reduces some of the oxygen content in the during the deposition. That's what is deep. Then the conductance values also that we can do, for example, the resistance values on the right, you can see if this 10K resistance is not exactly one line, it's a spread of resistance. And then you can have 4 distinguished areas. So that means you can do those dimensions on the weights that you can have multiple. This is actually already proven this one. We have published some work on this initial work. And to make a perfect device, we have to do this first of all. What is the power consumption? To reduce the power consumption, we have to have a right type of dielectric, which will follow. We will have right type of material, top metal, and right type of bottom electrode and top electrode. PE is top electrode, which is the top metal. And this is just a simple metal dielectric and metal simple device. So you can make it in nanoscale easily, but it has to work efficiently. So, okay, so what we did actually, we built a device, a simple device. The titanium nitride metal on the top electrode, then, and also there is a titanium on the top. We created 2 layers of material. One is hafnium oxide, one is aluminum oxide. And then, of course, the bottom metal of titanium nitride. The idea is here why we built these 2 layers, because based on the dielectric constant of this material, the field that you apply or the voltage that you apply across this device to be distributed differently. If the dielectric constant is very high, there will be low field across this dielectric. The dielectric constant is low, the high field will be. So this will create a lot of defects or the oxygen vacancies. Also the aluminum, in this case, aluminum can fuse to hafnium oxide, create this defect. And then we studied this device, what actually after the device is completed. These are real experimental data. After the device is completed, how aluminum is diffusing other things. Now here in this device, the blue line is the aluminum oxide and the green is hafnium oxide. And then we saw these devices start switching at 10 microamps, which is a lot of current after switch. And what we did, we flipped this position of this dielectric. We moved this aluminum oxide to the top and the hafnium oxide to the bottom, and then looked at what is the electrical characteristics. And then next, these devices started switching in 50 nanoamps. That is what happens, that we intentionally created, indirectly, we looked at some of these studies, same aluminum diffusion, same, aluminum has another problem or advantage. It breaks the oxygen aluminum bonding, the aluminum O3, very easily because of their activation energy breakthroughs compared to the hafnium oxide. So we'll have a lot of defects in the closer to the top electrode. So we saw that if you have a graded structure of distribution of oxygen vacancies in such a way, so it will have better characteristics or extremely low power. So these are some of the examples that I said. The activation energy is 4.6 electron volt inside hafnium oxide, but 1.8 electron volts in aluminum oxide. So you can go ahead. So as I mentioned, keep going. So this is a higher concentration of oxygen vacancy. What we summary that we found, a higher concentration of oxygen vacancy start with near the top electrode, that reduces significantly the switching power. Then we said, okay, if you use two dielectrics, it's very complex process. That also consumes lots, as I mentioned, we discussed about carbon nanotube. What we did, we deposited 3 nanometer of hafnium oxide, exposed this one to hydrogen plasma for maybe 30 seconds, and then deposited another 3 nanometer of hafnium oxide on the top. Created this device, we call them as a hafnium with treated device, the plasma treated device, and created the ruthenium metal on the top, then titanium nitride. This is the device, simple device we fabricated. And then, so what happened actually, when you deposit the second layer of metal, because of oxygen presence, it reduces the defects on the bottom layer and move all the defects to the top layer. That is our plan, which we learned from the bilayer structure of aluminum oxide. And that one, the bilayer structure, what we learned, the similar things to the graded distribution of oxygen. So that actually gives the same high concentration of oxygen vacancy near the top. And then we could switch this device in 3 nanoamps of current. But that is still high. If you 3 nanoamps, if they are looking at the energy in the picojoules, 3 nanoamps is very high. So we said, okay, let's look at this carefully, understand it better. So we played with also different metals in the top electrode. One is with ruthenium, one is with just titanium nitride, because ruthenium is expensive as well as it's very difficult to deposit and time consuming. So as I mentioned before, it is the 3 nanoamp, but if you change next to another one, this is actually 4 nanowatts of energy is required to switch this device back and forth. And because if you apply the voltage in one direction, it become low resistive state, and we switch the voltage, then it becomes high resistive. But with the ruthenium, it actually reduces from 15 nanowatts to 4 nanowatts. So the idea here is we studied the 12-inch wafer, hundreds of devices, and that is the. So the benefit that we got here to reduce the power consumption from the switching, we said, okay, we'll apply to other materials. Then we compared with, as I mentioned, we have many different with the bilayer, and with ruthenium, with all of them are actually ruthenium. But with hydrogen plasma, that devices we did, that has the lowest energy consumption. This is another set of devices we created. To run the device in a very reliable way, we applied around 120 nanowatts power to switch device, around 90 to 100 nanowatts. Next. So then, but that is just a DC measurement. So we got to do that when you use this in the circuits. What we did actually, we designed a pulse train operation. So we had a 4 microseconds pulse width. All these pulses are at height exactly up 2 volts. And the only thing we changed is we applied 4 microsecond pulse for 20 of them, 20 cycles. And then we changed to 50 microseconds and also apply for 20 of them. Like that, we go to 1 millisecond. And the interesting thing is, if you look at it on the left side, you can see 4 distinct conductance left with the 4 microseconds because it's less time, build some conductance, and we increase the pulse width. Simply increasing the pulse width, change the conductance of that material or the device to another level. So it is develop the conductance, different conductance states. So by adjusting the pulse width, one can actually determine exact conductance levels. Whereas in the device that is to the right, it has no defects. It was not exposed to hydrogen plasma. That's why these devices initially just jumped to one level. So this is actually we are trying to do. So then we have to study this endurance of this. Okay, this gave very nice quantization. Maybe next one. And we looked at that just simply changing few pulse width and you can see many conductance levels. But you know, those who are very close to each other, it's very difficult to manage them. We have, if you look at, you can have very good selecting selecting the pulse numbers on the pulse width, and have several of storage elements there. Next. And then looking at the endurance level, for example, if you have to go 10,000 times, we looked at which will maintain the without any variations. They got to have the exact same conductance throughout 10,000 cycles. And you can see for the 4 microsecond pulse, there is a drift, and also there is, if you go to extremely high pulse width, then also there is drift around 50 microseconds for these particular devices. We got to make sure that all the devices work properly and efficiently. This is one example that we got to study the endurance. As I mentioned, since we have graded structures, the graded distribution of the oxygen vacancy, we can do that. So we did the similar devices next. Studied 3 devices. What if we lower the concentration near the bottom left by 4? So we introduced some nitrogen at these the interface and near the bottom electrode. After this deposition, we use nitrogen there, and we can suddenly reduce to 100 picowatts of power. And that is actually just what we have considered with the same hydrogen plasma exposed hafnium oxide. Next. And that is because the nitrogen actually forms a better bond at the interface, and that's the physics of that. Why it's used the oxygen. Next. So then we looked at the zirconium oxide. Again, we took a device without any plasma. Then another case, the device B in this case is deposited zirconium oxide and exposed to hydrogen plasma on the top of it. Then came back to the middle part. We did several cap layers. The top layer we call it as a cap layer. We deposited 3.5 nanometer and exposed to hydrogen plasma, and again 3.5 nanometer. Next one we did also device D. Device D is that identical and just at midpoint. Device D actually we did 3.5 and the cap layer was 4 nanometer. And device C is the lower one is much thinner. I can see that 3 nanometer, right? 3 nanometer and 3.5. And we surprisingly found out that device D is only consuming 240 picowatts, the lowest. And so this is exactly the similar things that we have been studying those things now to look at, and then obviously we look at the pulse measurement next. Okay, this is called a forming power. So what we correlated here, if we apply the hydrogen plasma or without plasma hydrogen plasma, we see this leakage current. You can correlate very well the leakage current to see that the forming power actually goes down with the leakage. Some devices, we increase the leakage current too much, that device is dead. So it is like engineering the device fabrication in such a way and reproducible device. That's what we are working on now. And this is the cumulative probability, because you cannot show one data in millions of devices to see. We wish we could have more data, but for that we can see how they actually vary. The forming voltage, we look at the forming voltage. Initially, you apply a volt so that the device switches. After that, you can go back and focus the lower voltage. Initial voltage is the actual power consumption, maximum power consumption. So that means the summary of this we just published this month. This data we submitted. Published one paper, our student. We work with a company. So the process optimization of engineering the process conditions to optimize the device fabrication. That's all. Next. So the idea is now there is a new structure now. If you come up with materials, next you can just put 4 of them. Yeah, so now this new idea is how to do the designs, the code design. We cannot develop materials by itself without knowing the device. The device and material code design. You cannot have a device without knowing the circuits. So circuit device code design, and we cannot have circuits without knowing the system and system level. For example, if you have a graph neural network that you want to do, you've got to do the systems and circuit code design first, and then go to circuits and device code design. That's the goal now. And right now, there was something $500 million NSF has given last year alone to do this development, how to do code designs and come up with new materials and modify the code. That is one thing happens. So this is just the beginning of development AI hardware, just starting up. And these computer design tools developed, they are jumping in. The manufacturers also jumping in. So these will continue. The materials, instead of going to some new materials which is not compatible with silicon chips, that's why we use high-k dielectric. That is we focus now, even TSMC or this one manufacturing. Look, they are one pattern. The suitable dielectric processing to optimize developing a recipe that will be from high volume manufacturing. That's the goal. And as I mentioned, device, material to device, device to circuit and circuit systems. Okay, so that's all I think next. I will thank, I work with the Tokyo Electronics Center to go back. So that's okay. We work with the Tokyo Electronics. They have a certificate. Work with them. Luckily, they process the manufacturing. But whatever we suggest for the test device, they modify and process it. Several graduate students, some of them gradually working Dell and all the places, and also successors. Yeah. Okay, next. So that's all that now we can have this question.
Excellent lecture. Now I think we'll open it for some Q&A. Mr. Anant Kumar? Anant Kumar ji,
Uh, yes, sir. This is too high standard for me. I'm a mechanical fellow and bolt and nut man, but I was interested to see. Excellent lecture, sir. But I need to study quite a lot more and go much deeper into what you are doing. It is amazing that you are doing it nano level. So I promise you, I will study a little bit more in future. Thank you.
Somebody is going. Yeah. Sorry, sir, there is some. Okay, now we stop.
please actually,
Could you please ask the question again? You are asking something, we can just go for discussion, not necessarily question and answer. You have any?
Anant Kumar ji, repeat what you said, we couldn't hear.
No, I just said that I'm a mechanical engineer and essentially a nuts and bolts man. Can you hear me?
Yes, yes, we can.
I'm a nuts and bolts man. So mechanical engineer, I'm just trying to get ideas from you. I'm trying to understand what are the innovations you are doing in this. And it seems to be terrific, absolutely terrific. So I am amazed that so much is going on and you are looking at putting oxygen vacancies in zirconium and hafnium and various other materials. I am simply amazed how you are doing it. So what I need to do now is to study what you are doing, already studying, get at the literature, study more, and then try to understand a little bit more. I was trying to get at exactly what the kind of progress that is being made in this business, artificial intelligence business. So I have only real intelligence. I don't have artificial intelligence. So that's the
No,
problem.
no. Okay, thank you for your comments. What actually happens, the artificial intelligence right now in general, mostly software focused. But the software focus means if we do only on the software, even the chips that is coming out, the AI chips, they consume huge amount of power and not possible to scale. So that's why there is a new hardware approach has come. How to build these electronic devices. These transistors that will be there, they will still be there. How to make new devices in nanoscale, like 1 nanometer device, and it will work for us with extremely low power consumption. So there the direction is going. Innovation. It is not easy.
Will some of this research be done in India also or only United States? I don't know. So you said something like $500 million or something like that. So
Yes.
is the government of India planning to spend such money and then get on with manufacturing these things? Otherwise, we will be always dependent on buying these chips from somebody else.
In India, they are doing right now a lot of design work in the hardware design. But the manufacturing, we can send it there. India, they're sending it outside. There is no manufacturing at all. Also, there is no manufacturing research in India. Only thing is everybody wants to do research in the software. But there is an opportunity. There is an opportunity to do that research. For example, the devices that I was talking about, the introducing artificial intelligence to design new circuits. Those are actually is possible right now. How to use these large language models, which is available to everybody. But thing is, we have the brain power. So we can actually, in India, we can actually do those things. And making this a reality in the hardware or in the electronics chips or the systems is still a long way now.
Long ago, maybe about 20 years ago, I had a chance to talk to Dr. Kalam. He was at that time in DRDO. So he was trying to say that we want to make VSLI, large scale chips.
VLSI, yes.
I don't know how much VSLI. So how much they have come on that, I don't know. But India, we have lagged very much on making these chips. I don't know, somehow we have to improve that.
Yeah, making the chips is definitely needs improvement, but the government is willing to spend. I think the Indian government has decided to spend $16 billion to start manufacturing. I heard that Micron Technology has established something in Gujarat, build the memory chips. But besides that, nothing much because these companies have to invest huge amount of money.
So some beginning is good beginning. So I hope we will improve with time.
Yes, yes, it is. It is actually there is a big focus. There is a lot of interest on the semiconductor. So we were going to have a semiconductor sort of seminars. We are getting some experts from Stanford University and Georgia Tech and Cornell for the semiconductor in Odisha. Odisha, if we have one semiconductor manufacturing here, then it will build a large number of infrastructure around it. It build the ecosystem of the semiconductor manufacturing.
We had one semiconductor manufacturing, 6-bit chips, I think we were manufacturing in Semiconductors Limited in Chandigarh. And it got fired. They put a big fire on that, and the whole thing got engulfed. We have to restart that, I think.
It's back to operation now. They are doing 180 nanometer technology is working.
Okay, that's good.
Any other comments and discussion?
Okay, sir, Deepak sir, go to.
When I unmute, there is a echo coming up, so I'm not able to unmute. Anyway, am I audible?
Yeah, we can hear you. Yes.
Sir, just a simple question. I saw that you are measuring thicknesses in nanometer, picometer, and you are also measuring wattage in nanowatt and picowatt. I was wondering, what are the methods of measuring them?
What is the method of measurement? What is the question?
It is measurement through some no, the echo is disturbing me. I can't.
Okay, so you can mute it now. I understand. I can talk about it.
Yeah.
We have a new system that was created called this Agilent technology. They are giving us. We can measure even femtoamps of current through a device, and it's highly reliable. That's what we can estimate. This is in picoamps and nanoamps. So these are very easy to measure. How much power you actually need to start the device to switch. That's why our power estimation is the first one. Then after that, it requires low power, lower than the first power to operate switch back and forth for 10,000 lines. So that is our goal, how to reduce this device that requires low power switch. Because we will need 19 of them to be integrated together, make a function. That's why the idea. That's the measurement. You are talking about the measurement part that we use. It's called B1500. That is a semiconductor device measurement system. That's why we do. That's called nanowatt. And then the deposition of 3 nanometer of the solid 3 nanometer of the film done by atomic layer deposition. There is a new processing unit called atomic ALD, atomic layer deposition. There you go for by cycle mono layers, and you know exactly how much. And so that is a different new process that only 10 years. And that way we can achieve very precise. These are all done, they showed in one of the pictures, a huge machine. They are called the cluster tools. That means inside the machine, you deposit the film. Inside the same vacuum, you move the wafer and expose the plasma, bring it back and deposit it without taking it outside. This is all done by a lot of robots. No. Sir, you can now mute yourself. Dr. Tripathi, you can, yeah, now it's gone. Okay,
You are-
so this is, go
You
ahead.
are, you are using zirconium, hafnium like that. In
Yes.
your process, will heavier atoms help you? Atoms which are heavier than nuclei which are heavier than zirconium, hafnium and other things like that. Will it help?
No, heavier atoms will not help that much, but it will be more expensive to make them. The heavier atoms will, they have tried different materials already. And then they found out the heavier atoms is more expensive to make the resistive material or the switching material. And but it reduces the power reduction that it will give is not very significant compared to this. So that's why we're trying to do engineering these materials during the deposition and keeping them highly reliable. That is the idea. That's why, that was my knowledge.
Any other question? Anybody who would like to ask any question, please?
That's comment also fine. If you have any comments, please let us know. I try to make it simple. That's all.
Okay.
You have
But
any
no, but you are really trying to solve a very challenging problem, no doubt. Because it is a fact that we will be using more this AI tools and other things for future, which will be very, very power intensive. And the devices that you are trying to do is it will really reduce the power requirement.
That's right.
That is
Every level we have to reduce the power.
That is very, very important. Now, one more thing which Kumar asking that whether something is actually being done in India, but the fact remains, nothing is being done.
But maybe something may be happening in the research labs.
Research lab, something may be happening, but I think big things are happening, and even the manufacturing front, only they are trying to put actually now a sort of foundry in Gujarat. And that too also it is not really supported by a lot of R&D and all this. They are thinking that some technology they will get it from somewhere and start actually making.
Actually, I did one discussion with some scientists in the Indian Institute of Science. And asked the STEL executives, the Tokyo Electronics from Japan, they came and visited India. But what they told us, because I did that from the US base, the CEO, US headquarters, I talked to him, so he pushed the Japanese people to come, the main CEO of the company itself, CTO, Chief Technology Officer, and marketing team. But they found they don't have anything to do. That's what he told.
They are
He said there is no ecosystem now. Once you have several manufacturing facilities, they will come and build a research unit in IISc, for example, and then provide the recipes to this manufacturing. Recipe in the sense, the research they come up with exactly how to fabricate in their recipe. And they translate that thing to do optimizing their manufacturing.
That's what I would like to say. Even the Hinsu Science Park in Taiwan.
Yeah.
So where the lot of this semiconductor production is actually going on.
Yeah.
So that is actually supported by a couple of universities, where the basic research is actually
Yes.
going on there, and they are able to do the translate this thing. For example, at, one university that I have visited, they have actually a forgetting exactly, but it is in Hinsu only.
Yeah.
So they have got an experimental foundry in their thing.
Yes.
And then the students actually who pass out from there, they are actually employed by this
TSMC.
this, this into science park. That type of backup is actually not there in our case. Yeah, when we are talking of that, we have it in Gujarat. You can go ahead. And the question is where to get the people.
Actually, worst thing somebody mentioned to me that the research they're doing in the lab, they publish it right away in India. And they publish it means these ideas companies take and they use them in their process. They don't file patents. Then that's why there is no money comes to India. There is nobody who wants to monetize. They said, okay, we want to publish. We are doing it.
I think we are doing reasonably good work actually in the design part. And you can do that.
Yeah.
But the other part is
That has to happen in India for sure to have a self-reliant safety. Tomorrow, by chance, some people stop going a ship to India. We are good. And to be a good power, we need to have some level of high level.
You see, there is one more thing also. For example, I know HCL technology. At one time they said that we Foxconn actually will develop a
Assembly, there is assembly plant for iPhone. Yeah.
so basically a contract manufacturing firm.
Yeah.
They are not the fellows actually who can do this type of.
No, they are not the chip man. They are just assembly.
That assembly, that iPhone assembly, all the things they are doing here in India, so they can do it.
Yeah. Not the hardcore chips. They are still coming from South Korea or Taiwan.
Yes. Only thing in this front, very close to actually cut off. JSW Steel, they are actually putting one lithium ion battery manufacturing. And they're spending quite a good amount of money, about 40,000 crores. I think if that comes up, that will be a sort of major hardware company that you can.
That will be supplying to the all electric vehicles.
Professor Mishra would like to ask anything? Please unmute and ask. Unmuted us. Please unmute if you want to ask something.
Yeah, so,
Please unmute. Go to the top.
this the problem with Teams. Everybody.
Right.
Google is also good. Teams actually a good one. Reliable, but people cannot find it. Can you unmute?
Can you write? Is unmute.
No, that you can do, but he's
They niche koriପାରିବେ ସବୁ. Go to the top in the corner. You'll find there is a.
You can look in the top, you have a button there for unmute. The mic button.
That button you click, it will be.
No.
Anyway.
I have one question.
Conductors.
You're talking about conductance.
No, I'm just.
You talk conductance connect. This is connect. Also variable with faults.
Yeah.
So it really happens because of the current maybe is there a conflict or why is that?
No. What actually happens when you apply the pulse for certain duration? Some of these vacancy changes their path. That's all it happens. When you increase that, then you will give it a little longer time to build up. That is, I told that there is a there is a thicker, just makes the filament thicker. So the conductance goes up. You can see if you apply it a little bit longer and longer, that becomes thing. Then you reverse that thing, it comes back to
That content is.
yeah, resistance value. Okay. No, not into, I have not looked at that. Just understand how the release of oxygen atom happens from there, how they move. One good thing I did mention that put hydrogen there, forms hydroxyl groups. They help to pushing these oxygen atoms also and forming the oxygen vacancies, combining. Also, that actually we are looking at what is the fundamental physics behind it. There is some papers have published in theoretical currently. But I don't think there is any quantum mathematics going here because it's total 7 should be quantum. Yes, yes, it's happening there. But we are not going to that because we are staying in a
Macro.
we don't have to really go to quantum level to analyze.
Something like your brain synapse with some voltage.
Yeah.
Then higher.
Right. So if you have processed that level, then it will come. We can set up actual thing these weights based on the location.
Now I think we'll, Rohit, you can have a discussion.
Yeah, no, we will continue a lot of other things. Okay,
Madam, would you like to present a vote of thanks?
Yeah. You can get us a vote of thanks, yeah. It's not a problem. Not those powers.
No, just
Thank Mr. Really enlightening, entertaining talk. Really, I think we learned a lot, understand what's happening, how things can happen in.
you please take a photograph of this one. Madam, you please present the bouquet.
সেই বললে 350 রেটিং দিয়েছো
This is the power and give this
কোথায় আছে এটি
অন্যরা প্রেম করবে
আসলে তারা
Something that's never happened.
এই যে বড় ক্যামেরা এইতরে বড়
রেকর্ডিং হচ্ছে
রেকর্ডিং হতো কিন্তু এইতরে বড় ফটো নেই তারা আছে
এখন কিন্তু আমি খেয়াল ঠিক আছে
এটা সমাধান ওকে এটা বড় ফটো
না রাষ্ট্রে
এই ফোন নেবে টোটাল
Yeah.